Hello students, let us discuss about the asymmetric key cryptography. Unlike symmetric key cryptography, when we use two different keys for encryption and decryption, then that cryptography is known as asymmetric key cryptography. Let us discuss about the agenda of this lecture. First, we will be having a lecture on distinguish between two crypto systems, symmetric key and asymmetric key. After that, we will introduce trapdoor one-way function and their uses in asymmetric key crypto systems. After that, we will discuss about the hard problems. Basically, we will be discussing about two hard problems, integer factorization problem, and the next one is discrete logarithm problems. After that, we will discuss about the two asymmetric crypto system, that is RSA and EL-Gammal. We will be discussing about the setup of algo, encryption and decryption algo, and security features analysis of both the encrypting algorithms. In the end, we will finish this lecture with a discussion of digital signature. First we will introduce the asymmetric key cryptography. Symmetric and asymmetric key cryptography will exist in parallel and continue to serve the community. We actually believe that they are complements of each other. The advantages of one can compensate for the disadvantages of the other. The question is, even if we have symmetric key cryptography for the secure communication, then why we are going with the new crypto system, that is asymmetric key crypto system? Then the answer is, they both are complements of each other. The advantages of one can compensate for the disadvantages of the other. That's why we are using both. What topics we will discuss in this section? First, we will discuss about the keys, general idea, need for both, and then trapdoor one-way function. I have written down one note here. Symmetric key cryptography is based on sharing secrecy, and asymmetric key cryptography is based on personal secrecy. What does it mean by? Sharing secrecy means sharing the secret key before actually sending the message. In symmetric key cryptography, for the secure communication, we have to send first the secret key to the receiver, and after that we send the message to the receiver. But in asymmetric key cryptography, there is no need to send the secret key. Actually, everyone has his own private key, and using that only they decrypt the message. Asymmetric key cryptography uses two separate keys. One is known as private keys and one is known as public keys. Public key is known to all and the private key is known to only the user. Let us discuss about the locking and unlocking mechanism in asymmetric key crypto system. Suppose Alice wants to send to the message Bob. Then Alice has to encrypt the message using the Bob's public key, and he sends it through the insecure communication medium. And when Bob receives this message, he decrypts this message using his own private key. If any message is encrypted using the public key, then that will be decrypted using the private key, and vice versa. So what is the basic general idea about the asymmetric key crypto system? Let us suppose Alice wants to send message Bob. The public key of the receiver is known to everyone. Alice receives the public key from the public key distribution channel and encrypts the message and sends it through the insecure channel to the Bob. And when Bob receives this message, he uses some key generation procedure, or we can say key generation algorithm, and generates his private key, and using that private key he decrypts that message and reads the plain text. As we have seen that we were not using integers in the case of symmetric key cryptography, but unlike symmetric key cryptography, in asymmetric key cryptography, plain text and cipher text are treated as integers. Encryption algorithm basically takes two parameters, public key of the receiver and plain text, and gives cipher text as a output. The decryption algorithm uses two parameters, private key of the receiver and the received cipher text, and gives plain text as a output. Now we will be discussing about what is the need for both symmetric and asymmetric cryptography. The use of both symmetric and asymmetric cryptography and keys are part of well-rounded solution for securing digital transactions. Each approach to protecting data has its benefits, especially when applied to the appropriate scenarios. Here we look at the reasons for using each cryptographic method. For standard encrypt decrypt functions, symmetric algorithms generally perform much faster than their asymmetric counterparts. This is due to the fact that asymmetric cryptography is massively inefficient. Symmetric cryptography is designed precisely for the efficient processing of large volumes of data. In other words, symmetric encryption is generally used for speed and performance. When there is large amount of data that needs to be encrypted using symmetric key systems. When there is when there is a less amount of data, then you can go with the asymmetric crypto systems. Asymmetric is more beneficial when larger subsets of entities are sharing informations. While asymmetric cryptography is relatively expensive when it comes to computation part, it works well in situations requiring the benefits of public key infrastructures. A common example is when a trusted connection needs to be established where there is not an existing shared secret. So we have studied that why we use both type of crypto systems. Now we will be discussing about the trapdoor one-way function. The main idea behind asymmetric key cryptography is the concept of trapdoor one-way function. First, let us discuss about the function. Function is nothing but a rule to map the values from one set to another set. The values which are mapped to the other set, that is known as domain, and the mapped values is known as range. Function takes values one by one from the domain and maps it to the range. And the inverse of function, what is the inverse of function? Let us suppose here in this sheet we are presenting a function y equals to fx. Then if we are known the value of x, then we compute y. It is known as direct function. But if we want to calculate inversely, like if we are given y and we have to calculate x, then that is known as f inverse. One-way function. In one-way function, f is easy to compute, but when it comes to calculating the f inverse, it is difficult to compute. Here, trapdoor one-way function play a major role for the asymmetric cryptography. Why? A trapdoor function is a function that is easy to compute in one direction, yet difficult to compute in opposite direction without the special information called the trapdoor. What is trapdoor? Trapdoor is a small door in the main door using which we can enter into a house. So trapdoor is a hint to solve any inverse function. Basically, in mathematical terms, if f is a trapdoor function, then there exists some secret informations a such that given fx and a, it is easy to compute x. An example of a simple mathematical trapdoor is product of two prime numbers. If we talks about the question what are those numbers, then it is very difficult to find the both the numbers which are making the product of the actual number. A typical solution would be to try to dividing that product by several prime numbers until finding the answer. However, if one is told that one of the numbers is this and this, then he can find answer by dividing the second number by the first number. So basically, if we use some hints to calculate the f inverse, then that is known as trapdoor function. Let us see some examples on the trapdoor function. When n is large enough, then n equals to p into q is a one-way function, because given p and q, we can easily calculate n. But when it comes to when we are given with n and we have to calculate p and q, then it is very difficult to find out the value of p and q. This is known as factorization problem in mathematical terms. The next example of one-way trapdoor function is when n is large, the function y equals to x to the power k mod n is a trapdoor one-way function. If we are given x, k and n, then we have to find the value of y. It is direct function, but when it comes to calculate the inverse of this function, like we are given y, k and n and we have to calculate x, then it will be very difficult task to find the value of x. This is known as discrete logarithm problem. However, if we know the trapdoor k dash, trapdoor is a hint to calculate the inverse. In this example, if we know the trapdoor k dash such that k into k dash equals to 1 mod phi n, then we can easily calculate the value of x by using this formula, x equals to y to the power k dash mod n one-way trapdoor one-way function is a key part in asymmetric key cryptography, because it is very difficult to guess any values in the when we use the f inverse. But Also at the same time we have to calculate the F inverse. If anything is being used by some hints, then that is known as trapdoor, and using that trapdoor, if anyone knows that trapdoor, then anyone can easily calculate the inverse part of the function. So now let us discuss about the hard problems. In mathematical computations, hard problems are, or intractable problems are those problems which take unreasonable time to be solved, regardless of hardware on which it is being implemented. Now let us talk about the complexity classes of different problems. A problem comes in P class if it can be solved in polynomial time. All those problems is called polynomial time algorithms if it can be solved in polynomial time. NP is the class of non-deterministic polynomial time algorithms for which a solution can be verified in polynomial time even though the solution may be hard to find. Means NP is non-deterministic polynomial time algorithms. Those algorithms can be solved in polynomial time, but the solution may be hard to find. The next class is NP complete problems. In all the complexity classes, the problems comes under this class is the hardest problems to be solved. We don't know how to solve them in polynomial time, but they are all equally hard. An efficient solution for any one NP complete problem can be used to solve all the other NP complete problems in the class. What is the use of these complexity classes in practical cryptography? If breaking a cipher were NP complete problem, that would be a very strong cipher, but NP complete problems are impractical for cryptography. Why? Because they are easy in specific cases. So real cryptography uses problems that are probably not NP hard. In the category of hard problems, there are two problems comes. First one is integer factorization problem, and the next one is discrete logarithm algorithm. Now let us talk about the integer factorization problem. This integer factorization problem is stated as a search problem. Given an integer n, to find its prime factors is known as integer factorization problem. To solve this, we apply a brute force approach. In brute force approach, we traverse through all the numbers which belongs to the interval 2 to root n, and we verify every single number which divides n. So in this class, we need to consider at most root n numbers of for divisions. Let us suppose that we are using k bits number to find the prime factors of a k bit number. We might have to consider 2 to the power k upon 2 possibilities. For to show the hardness of this problem, we can consider an example. Given a 150-bit number and a p-flops capable supercomputer, time needed to find its factor was almost 1 year. So you can imagine how hard to find the prime factors of a big and bigger prime numbers. In RSA cryptography system, typically we uses 1000 bits for its number. So you can imagine if we were using 150-bit number with a supercomputer, then it was taking almost 1 year. Then if you use 1000 bits in RSA, then you can imagine, and even though if you are using supercomputers, then you can imagine how long time it will take to find the factors of a 1000-bit number. Integer factorization as a decision problem. Given two integers a comma k, we have to check that if there exists a prime number p such that p belongs to 2 to k, then we have to check whether p completely divide a or not. The first instance is yes instance. Yes, in this instance we can find a prime number p that satisfies the above requirements, and the next instance is no instance, which signifies that we cannot find any prime number that satisfies above requirements. After seeing this integer factorization problem as a decision problem, we can clearly say that integer factorization problem comes under NP problems. But whether it's NP complete or not, the question is whether it's NP complete or not, then we can say that it's not known to be NP complete. So we can use this integer factorization problem in asymmetric crypto systems. Let's discuss about the next hard problem, that is discrete log problem. In discrete log problem, types of cyclic groups which is used is ZP, and the operation which is used is multiplication. So it is represented as ZP asterisk. Discrete logarithm problem in ZP asterisk is known as, we will explain what's the statement of discrete logarithm algorithm. Suppose we have a finite cyclic group ZP asterisk of order p minus 1 and a primitive element alpha which is belonging to ZP asterisk, and there is another element also present there, beta, which is also belonging to the ZP asterisk. The DLP is the problem of determining the integer ranges from 1 to p minus 1 such that alpha to the power x is congruent to beta mod p, or in other words we can say that x equals to log beta base alpha. Above computation is called the discrete logarithm problem.
Okay, now we will see the RSA crypto system. So it is a public key algorithm that was invented by three inventors, that are Rivest, Samir and Edelman. So it is an algorithm used by the modern computer system to encrypt or decrypt the messages. It is an asymmetric cryptography algorithm, which means it uses the two different keys for encryption and decryption. Like in symmetric key cryptography, we uses the same key for encryption and decryption, but here we will use the two different keys for that. It is also called as a public key cryptography because one key is made as a public and other key is kept as a private. So this algorithm is basically based on the fact that finding the factors of the large composite number is difficult. This algo uses a key pair of public key and private key. Public key is used to encrypt the messages, and to decrypt the message we use the private key. Let us take a scenario where Alice wants to send a message to a Bob, and there are two options they can use, like if she wants to make sure that whatever he is sending to the Bob, it is not readable by any other person, so he can encrypt the message and send it to the Bob. After that he can decrypt. So for that he can use symmetric key cryptography, for which there is a symmetric key that will be used for both encryption and decryption. But here we can use a asymmetric key cryptography, for which there will be a key pair for the public key and the private key. The public key is used for the encryption and the private key is used for the decryption. So here public key is, in this figure you can see, like E is a public key and D is a private key. So what Alice will do, like he will encrypt the message, a plain text P, with the help of that public key, and get the cipher text. And after that the cipher text is sent to the Bob through a insecure channel through a internet. By using that private key D, he will get that plain text. So through this asymmetric key cryptography they can communicate. But here is the third person, Eve, who will interfere between the conversation. Like he will, let us suppose he get the cipher text in between, and he tries to get the plain text for that. So what he will do, like he will calculate the plain text by using the eth power of c mod n. So like when Alice will compute the cipher text, it is a polynomial time. He can calculate the cipher text in a polynomial time, and also the Bob can decrypt the message in polynomial time. But when Eve will try to get the plain text using that cipher text only, when he do not know about the private key, so he will use this formula. So you can see that it is a exponential time problem. So it is almost impossible for him to solve. So let us move to the next slide. Like here you can see the encryption and decryption. Like here Bob will do some calculation for that, and he will get the E and D, that is the public key and private key, and value n. What he will do, like he will make the E and n as a public, so that anyone who wants to send a message to a Bob, he will use the E and n and he can send the message. And also he will keep the D as a private, so that he can decrypt the cipher text with the help of that private key. So here you can see, like Alice get that E and n, and with the help of this E, he encrypt the message and get a cipher text. The ciphertext is sent to the Bob, and Bob, with the help of that private key, can decrypt the message and retrieve the plain text for that. So, okay, for better understanding of the RSA algorithm, let us take the another scenario, like where Alice and Bob are communicating. So, for establish a communication between them, Bob needs to make some calculation to start the communication. So, like he will generate the E and D and the N, where E is a public key, D is a private key, and N is the multiplication of the P and Q. Later I will tell you what is that P and Q and N. In the coming slides you will be knowing about that values. First, let us think like he makes some calculation and find out the E and N, and E and N will make it as a public, so that anyone who wants to send a message to Bob, he will take these values, encrypt that message, and send it to the Bob. On the other hand, if Bob wants to read that message, then he will use this private key D to decrypt that message, and he can retrieve the plain text for that. So what is happening in this scenario, like Alice gets that these E and N, that are public. So using this E value, that is the public key, she encrypt that plain text P to the power E mod N, and gets a ciphertext for that. And the ciphertext is shared by a insecure channel, where anyone can intercept with that ciphertext, but he or she cannot predict the plain text, because he is not aware about the private key. Only the one who knows the private key corresponding to this public key can only predict the plain text. So when the ciphertext arrives at a Bob's end, so Bob will use this private key to decrypt that message and gets this plain text. What is there what is there in R? So it is an commutative ring, that the encryption and decryptions are done using the commutative ring with the two arithmetic operations, that are multiplication and addition. Now we need to know like how this public key and the private keys are being generated. So let's go to the next slide, that is the RSA key generation algorithm. So where, like, first of all there are some steps that are followed one by one. So like first step is to select a large prime numbers, two large prime numbers, that are the P and the Q. They should be large enough, that is there is some reason for that. So after that we will calculate the N, that is the multiplication of that both the prime numbers P and Q. After that we will calculate the totient value, the phi n, that is the P minus 1 into Q minus 1. After that we have to choose a value E such that it should be greater than 1 and less than phi n. So it should be lies between 1 to phi n, and it should also be a co-prime to phi n. That means there should not be any common factor between E and phi n. So you can, on the other side, you can, in other words, you can say like the GCD of E comma phi n is 1. So for calculating the private key, what we need to do is like D is congruent to e to the power minus 1 mod of phi n, or we can say like ED is congruent to 1 mod phi n. So with this equation we can calculate the private key and the public key. So after following these steps, we can get the public key and the private key, that are E comma N and d comma n, that are used, like public key will be used on the encryption side to encrypt the data, and the private key will be used to decrypt the corresponding data. There are some basic requirement of the RSAs. So here you can see, like, it is a public key, it is a private key. So if you are encrypting a message, then it should only be decrypted by the corresponding private key only. So with this equation you can understand it, like first we are encrypting the message, after that we are decrypting it using the corresponding private key, so we will get the same message for that. The second is, like, a given public key, it should be impossible to compute a private key. Like if you came to know about a public key, so by knowing only the public key, you should not be able to compute the corresponding private key. So these are the basic requirements of that. Let us come to the example for that, so that we can understand the RSA algorithm better. So what was the first step was to choose the two prime numbers. So let us take some small values to make the calculation easier. So here we have taken the P and Q as 7 and 11, and after that we have to calculate the n, that was P into Q, so n will be 77. In the third step we have to calculate the phi n, that is P minus 1 into Q minus 1, so it will be 60 in this case. After that we have to choose the E, that is the public key. So for that there is a condition that here you can see, like, E and D should be from this group only, Z60, so they both should lie in this group only. In the fourth step you can see, like, if we have to choose the public key E, so it should lie between 1 to phi n. Phi n in this case is 60, so it should lie between 1 to 60 only. So and the other condition was it should be co-prime to 60. So let us take some value. In between you can choose any values, and it should be prime also, so it should be prime also, so you can choose anything. Like let us take 3 in this case. So if we choose the E to be the 3, but 3 is between 1 to 60, but it fails in the second condition, like 3 is not a co-prime to the 60, because it divides the 60, so 3 cannot be chosen as a public key. After that we can try 7 value. 7 is already there, so we can, like, 5 can also divide it, so we cannot choose the 5. After that 11 is there, and after that only 13 is there, so we will choose 13 as a prime, as a public key. So let us suppose the E is 13, okay, and after that we have to choose the D value. So for that you might have remembered the formula. So ed congruents to 1 mod phi n, so it should satisfy that equation. So you can take the D as a 37. Like what we can do in this case, we can do, like, we have to calculate the D value. We know about the E as to be 13 in this case, so we have to find the D. Both are the multiplicative inverse of each other, so D should be such that, like, if we multiply that, it should give a remainder as 1. So here we can get D to be 37. If we, for making the calculation easier, you can see like we have to find out a such value that after multiplying with the 13 gives us 61. We can try this. If it is not, then we can try to be a 121. So like this you can check one by one every value and you can predict D. So in this case you only need to try like in first time you will try D as it should multiplied by 13 and give 61. If it is not giving, then you can try 60 into 2 plus 1, 60 into 3 plus 1, 60 into 4 plus 1, and so on. And accordingly you will put the D value, and whatever the result, whatever will give the result as 1, you can take that value. In this case, let us suppose it is 37. So after using this value, you can get the cipher text as 5 as 26. So here you can see like you have the plain text as a 5 and 5 to the power 13 mod 70 mod 60, so it will mod 77, it will produce the cipher text as 26. This cipher text is sent to the Bob, so Bob can use this value and get the plain text. So you can check like whatever the cipher text is sent, this is the 5 is the plain text and corresponding 26 is the cipher text. If we apply the same private key on that, 26 is the cipher text, corresponding 5 is the plain text. So both you can verify. Now let us see the attacks on the RSAs. So it has been seen like, and there is no such attack has been found that can destroy the RSA crypto system. But the several attacks have been predicted based on the weak plain text, weak parameter selection, or due to the inappropriate implementation. Some of them are like the factorization, the choosing ciphertext, the encryption exponent, the decryption exponent, and the plain text, modulus, and implementation. So let us understand one by one. Let us understand first the factorization. So attacks on RSA, the factorization attack. So here you can see the securities of the RSA is based on the idea that the modulus is so large that it's infeasible to factor it in a reasonable time. So let us take a scenario where Bob select the two prime numbers P and Q and calculates the n that is made as a public, but the P and Q are kept as a secret. If Eve can factor n and obtain the P and Q, so she can calculate the phi n also, phi n that can be derived by the P minus 1 and Q minus 1. If Eve Eve then can calculate the D also. D is congruent to e to the power minus 1 mod phi n, because the E was public, so he can derive the D also. When he knows the private key, then he can decrypt the message. So that is how with the help of the factorization attack we can get the plain text. So to secure the RSA, we require presently what we can do is like we can select that the value as a large, at least it should be at least 1024 bits, so that we can avoid this factorization attack. When the value will be large, it will be difficult to perform the factorization. Like when we have the n is this much large, then it will be infeasible to get the factors P and Q. So this way we can avoid this factorization attack. The next is the choosing ciphertext attack. So Like a potential attack on the RSA is based on the multiplicative property of RSA. So assume that the LSA, like the LAs, create the ciphertext C and send this ciphertext to the Bob. Also assume that the Bob will decrypt an arbitrary ciphertext for Eve other than this ciphertext that is sent by now. So Eve interprets the C and uses some steps like what are there. What he will do, like Eve will choose a random number, that is X. It will lie in the group Zn, and he will calculate the y with this formula, like C multiplied by X to the power E mod n, where E is the public key. So after calculating this value, Eve will send y to the Bob, and Bob will decrypt that and get this Z value. So like now if Bob has calculated this Z value, then you can see like it has been the chosen ciphertext attack has been performed. How you can see, like now the Bob can like the Eve can easily predict the ciphertext, where you can see like Z has been given as this, and whatever you have got previously, the by value you put it here. So Z is equals to C into X to the power E and whole to the power D mod n. After solving this equation, you can get like you can hereby see like this is already equal to the previous value. So the next is the encryption exponent attack. This attack is performed basically when we use the small encryption exponent to reduce the encryption time. Since this attack doesn't result in the breakdown of the system, but still we need to avoid this kind of attack. So the recommendation is to use the E as the 6537 or a very close value to this. For the decryption exponent attack, there are the two kinds of decryption exponent attack, that is the revealed decryption exponent and the low decryption exponent. In case of the revealed decryption exponent, like when the decryption exponent is revealed to the other user, they can easily get the plain text by using the decryption exponent. So in the RSA, in such case in RSA, if D is compromised, then the suggestion is that we should change all the values regarding. So the P, Q, and E and D must be regenerated whenever the D is compromised. So all these values should be regenerated to avoid this kind of attack. The second is the low decryption exponent attack, where we use the very low decryption exponent to reduce the decryption time. As in case of the encryption exponent, we use it to be a very low to reduce the encryption time. Here also we try to reduce the decryption time. So the recommendation for that is like it should be at least D should be at least 1 by 3 n to the power 1 by 4, so that we can prevent the low prevention exponent attack. So the next is the plain text attack. So there are the two short message attack and the cycling attack. So in the short message attack, if Eve knows the set of the possible plain text, she then knows one more piece of information in addition to the fact that the ciphertext and the plain text are the permutations of each other. So Eve can take the advantages of that. So Eve can encrypt all the possible messages until the message is same as the intercept he has got, the ciphertext he has got. So for example, if it is known that the Alice is sending a 4-digit number to Bob, so you can easily try the plain text numbers from 4 times 0 to the 4 times 9 to find out the plain text. So uh, therefore the short message must be padded with some random bits at the front end and at the end of the message. So it is strongly recommended that the message should be padded with some random bits before the encryption. The next is the cycling attack. The cycling attack is based on the fact that if the ciphertext is permutation of the plain text, so the continuous encryption of the ciphertext will eventually result in the plain text. In other words, if Eve continuously encrypts all the intercepted ciphertext, she will eventually get the plain text. So, however, Eve does not know what is the plain text, so she does not know when to stop. She needs to go one step further. When she gets the ciphertext, she goes back one step to find the plain text. So the next is the timing attack. So basically the timing attack is an decryption attack. It uses a fast exponential algorithm. So only squaring if the corresponding bit in the private exponent d is 0, so it requires the shorter time to decrypt. So both squaring and the multiplication, if the corresponding bit is 1, requires a longer time to decrypt. So basically we can say that the timing difference allows the Eve to find the value of the bit in D one by one. So the next is the powering attack. So basically the power attack is similar to the timing attack. So since the Kocher has showed that if Eve can precisely measure the power consumed during the decryption, she can launch a power attack based on the principle discussed for the timing attack. An iteration involving the multiplication and the squaring consumes more power than the iteration that uses only the squaring. The same kind of technique used to prevent the timing attack can be used to reduce the power attack. So here what we can do is there are the two methods to stop the timing attack. Like first we can add the random delay to the exponentiation to make each exponentiation take that same amount of time. The second is the blinding. So we can multiply the ciphertext by a random number before the decryption. So here you can see that. And there are the following recommendations to use the RSA algorithm. Like the number of the bits for n should be at least 1024, and in decimal format it should be 309. And when we are choosing the prime numbers, it should be at least 512 bits long, and the difference of the p minus 1 and the q minus 1 should have at least one large prime factor for that, and the ratio should not be close to a rational number with a small numerator or the denominator. And the sixth is the modulus n must not be shared, and the value of the e should be 2 to the power 16 plus 1 or a value close to this. And if the private key d is leaked or compromised, so the Bob must immediately change n as well as both the e and the d, the public key and the private key. So it has been proven that the knowledge of the n and pair e and d can lead to the discovery of another pair of the same modulus. So whenever the d is disclosed, all the values should be changed immediately so that the further messages are not being decrypted. And the last is the message must be padded with some extra bits or with some random values to avoid the short message decryption.
So in this section we will discuss about brief overview of EL-Gammal crypto system and its procedure, proof, analysis, and lastly security and application. EL-Gammal crypto system is another asymmetric crypto system or public key system which is named after its inventor Taher EL-Gammal, and its security basically based on discrete logarithmic problem. So let's recall the discrete logarithmic problem. If P is very large prime number and E1 is in the group of G which is belongs to ZP star and R is the integer. Okay. So first of all, let's know about ZP. Here P is prime number, so the values of ZP lies between 0 to P minus 1, but the values of ZP star is lies between 1 to P minus 1. Okay. So here if E1, R and P is given, so it is very easy to compute the values of E2 by using the formula E2 equal to E1 to the power R mod P. Okay. But if the value of E1, E2 and P is given, in that case it is very difficult to compute the value of R. So this is the overall of discrete logarithmic problem. So here let's see the example. Here as you can see, if P is large value, here E1 equal to 2, E2 equal to 1 and P equal to 283. Okay. So if we apply that formula, and it is very difficult to compute the value of R in that case. Okay. But if P is very small, so in that case we can easily compute the value of R. As you can see from the example, here E1 equal to 2, E2 equal to 1 and P equal to 3. Okay. So by applying the formula 1 equal to 2 to the power R mod 3. Okay, here as you can see it is obviously R equal to 2 because 2 to 2 square equal to 4. So 4 mod 3 is equal to 1. So we can easily compute the value of R in that case. So let's move on to the EL-Gammal crypto system. As we know, in asymmetric cryptography, if A wants to send the message to B, A needs the public key of B to encrypt the message, and B decrypt the message by using B's private key. Okay, so the same scenario is here also. As you can see, if Alice wants to send the message to Bob, Alice needs the first public key of Bob. Okay, so Bob needs to generate first public key and private key pairs. So here in the key generation phase, Bob selects a prime number, large prime number P, and then selects a primitive root E1 which is belongs to ZP star. Then it selects a private key D, and then it calculates E2 equal to E1 to the power D mod P. Here D is the private key. Okay, and the public key is here E1, E2 and P, and send it to the Alice. Now Alice, by using that public key, it encrypt the message C1 equal to E1 to the power R mod P. So here R is the random integer, and C2 equal to E2 to the power R into P mod P. So here capital P is the plain text and small p is the prime number. Okay, so this is the encryption phase. So the encrypted message Alice sends to the Bob. Now Bob decrypt the message by using Bob's private key by using the formula C2 into C1 to the power D whole inverse mod P. So this is how the encryption and decryption takes place in the EL-Gammal crypto system. Okay, so this is the key generation algorithm. As you can see, in the key generation algorithm, it selects first a large prime number P, then selects a private key D which is a member of the group G ZP star, and the values of D is lies between 1 to P minus 2. Okay, then it selects a primitive root E1 which is also belongs to ZP star. After that it calculates E2 equal to E1 to the power D mod P, and here is the public key. As you can see, E1, E2 and P, and private key is the D. Then it returns the public key and private key. Okay, this is the key generation algorithm. Now let's move on to the EL-Gammal encryption algorithm. So here the parameters records are, as you can see, E1, E2 and P is the prime number and capital P is the plain text. Okay. So first it selects a random integer R which is also belongs to ZP star. Then it calculates two ciphertexts C1 and C2. C1 equal to E1 to the power R mod P and C2 equal to P into E2 to the power R mod P. Okay, and returns this C1 and C2. So after that, here is the EL-Gammal decryption algorithm. So here the parameters are private key, private key and the prime number and C1 and C2 ciphertext. Okay, so it decrypts the message by using the private key D. So here the plain text equal to C2 into C1 to the power D inverse mod P and return the plain text. Okay, this is the overall encryption, decryption and key generation phase in EL-Gammal crypto system. So now move on to the EL-Gammal proof of EL-Gammal crypto system. Here in the decryption phase, to decrypt the message we need to calculate these parameters, that is C2 into C1 to the power D inverse mod P. So here C2 equal to, in the encryption phase, C1 equal to, we know that E1 to the power R, so we put the value of C2 equal to P into E to the power R, so we put the value of C2 is here E2 to the power R into P. Okay, and C1 equal to E1 to the power R, so we put the value here E1 to the power R and D is multiplied here, so E1 to the power RD and whole inverse and mod P. Okay, now again we know that E2 equal to, in the key generation phase, E2 equal to E1 to the power D, so we put the value here E2 equal to E1 to the power D, so R is also multiplied here, RD into P into E1 to the power RD inverse. So E1 to the power RD and E1 to the power RD inverse cancel out, so we get the plain text. Okay, this is the correctness of the EL-Gammal crypto system. Okay, let's see one example. So here Bob chooses a prime number 11 and E1 primitive root equal to 2 and private key is 3. So E2 equal to E1 to the power D, which is also given 8. So the public keys are 2, 8, 11. Okay, and the private key is 3. So Alice chooses random integer R equal to 4, and now we need to calculate value of ciphertext C1 and C2 for the plaintext 7. Okay, so here to encrypt the message we need to calculate two ciphertext C1 and C2. So by using C1 formula of C1 is equal to, formula of C1 is actually E1 to the power R mod P. So here E1 is given 2 and R is also given 4, so 2 to the power 4 is 16 and mod 11, prime number is given 11, so 16 mod 11 is 5 mod 11. Okay, and then we calculate the ciphertext 2, as you can see, P into E2 to the power R, so plaintext is given 7, so 7 is multiplied with E2 to the power R, E2 is also given 8 and R is here 4, so 8 to the power 4 is equal to 4096. So after that after the calculation we get the 6 mod 11. Okay, so here the ciphertext will be 5 and 6. So now Bob receives that ciphertext 5 and 6 and calculates the plaintext. So formula is here, as you can see, C2 into C1 to the power D inverse mod 11. So 6 into C1 to the power D is 5 cube inverse mod 11. So after calculation we get 7 mod 11. So 7 is the plaintext, we can verify that. So in the decryption phase, to decrypt the message we need to calculate the multiplicative inverse. So to avoid the calculation of multiplicative inverse, we can use this formula also, plaintext equal to C2 into C1 to the power P minus 1 minus D mod P. So this formula is basically comes from the Fermat's Little theorem. So here from the previous example, if we apply this formula, P equal to 6 into 5 to the power 11 minus 1 minus 3 mod 11. Ultimately we get the same answer, 7 mod 11. So next move on to the security of EL-Gammal. So here, if prime number p is not large enough, so in that case low modulus attacks may possible. Okay, as I have already said in the discrete logarithm problem slide, that if value of p small, in that case it is easy to compute the value of r, and we have also see the example also. As you can see, if e1 equal to 2, e2 equal to 1 and p equal to 3, so we can calculate the value of r easily. As you can see, that is r equal to 2. So in the key generation, in the EL-Gammal key generation phase, we calculate e2 equal to e1 to the power d mod p. Okay, so if p is not large enough, so we can easily calculate the private key d. So because of this, low modulus attack may possible. Okay, so it is recommended that prime number at least of 1024 bits or 300 decimal digits. Okay, so the security of EL-Gammal crypto system is basically depends on the discrete logarithm problem. Okay, now come to the non-plaintext attacks. So if the these attacks may possible if the random exponent r is same for the two plaintext p and p dash. Okay, so if can easily discovers p dash if she knows p. Okay, so for the plaintext p, ciphertext will be c2 equal to p into e1 to the power r mod p. Okay, and for the for the plaintext p dash, ciphertext will be p into p dash into e1 to the power r mod p. So now if can finds the p dash by calculating e2 to the power r equal to c2 into p inverse mod p, and then p dash equal to c2 dash into e2 to the power r inverse mod p. So this is another attack may possible if the random exponents r is same for the two plaintext. Okay, and so here is the note. As you can see, for the EL-Gammal crypto system, p must be at least 300 digit and r must be new for each encipherment. Okay, so now come to the this is the real this is the realistic example. As you can see, Bob uses a random integer of 512 bits. The integer of p is a 155 digit number. The ideal is 300 digit. Okay, so Bob then chooses e1 d and calculates e2 as shown in below. So here, as you can see, the prime number is so large, is almost 155 digits. Okay, and e1 equal to 2 and d is by calculating the by choosing private key d is 1007, and then it calculates e2, which is also so large, as you can see. And after that, Alice has the plaintext p 3200 and it will send to the Bob, and she chooses r random integer, as you can see, 545131, and calculates ciphertext. Okay, so here p is 3200, r is the this, and here, as you can see, c1 and c2 is so large, 88729 is almost so large, and almost 300 or 200 digits. Yeah, and Bob calculates the plaintext p equal to c2 into c1 to the power d inverse mod p, which is equal to 3200 mod p. So this is how the plaintext can be decrypted, and this is a realistic example. So now come to the application. So EL-Gammal can be used whenever RSA can be used. Okay, it is used for the key exchange algorithm and authentication, encryption and decryption for small messages. Okay, so this is all about EL-Gammal crypto system. Now come to the summary of EL-Gammal crypto system. So it is based on the discrete logarithmic problem, and encryption and decryption in EL-Gammal use the group of G, which is belongs to ZP star, and the public key is basically two exponent e1 and e2, and the private key is an integer d. And the security of EL-Gammal is based on the solving of discrete logarithmic problem, and low modulus attacks is possible if p is not large enough, and non-plaintext attacks may possible if r is same for two plaintext p and p dash. Okay. So students, in this chapter we are going to study about digital signature. First we define about digital signature and then we will discuss about its security services. Okay. So when Alice sends a message to Bob, Bob needs to check the authenticity of the sender. So Bob needs to sure that this message comes from Alice or any attacker. Bob can ask Alice to sign the message electronically. We can say that digital signature proves the authenticity of Alice as the sender of message. Okay, so now let's see the difference between conventional signature and digital signature. A conventional signature is included in the documents. It is a part of the documents. But when we sign a document digitally, we send the signature as a separate documents. So let us discuss one example. Suppose you want to withdraw a money from your account, then the bank employee will ask you to give your signature. Okay, so that he can verify your signature with the previously saved signature. And only after verification he will allow you to withdraw the money from your account. So he wanted to make sure that you are the real account holder. So your signature is basically used to authenticate you are the real account holder. Okay, so this is the example of conventional signature. But for a digital signature, the recipient receives the message and the signature. Okay, and after that, the recipient needs to apply a verification techniques to the combination of message and signature to verify the authenticity. So the digital signature is basically a mathematical scheme that is used to authenticate the sender of electronic documents, and it is a nothing but an attachment to any piece of electronic information which represents the contents of the documents and the identity of the owner of that documents uniquely. So let's discuss the digital signature process. The sender uses the signing algorithm to sign the message, and the message and signature is sent to the receiver, and the receiver applies the verifying algorithm to verify the message. So here, okay, let's recall the public key crypto system. In public key crypto system, if Alice wants to send a message to Bob, Alice needs a public key of Bob to encrypt the message, and Bob decrypt the message by using Bob's private key. But in case of digital signature process, if Alice is a sender and Bob is a receiver, then the message is signed by using Alice's private key and send the both message and signature to the Bob, and Bob applies the verifying algorithm by using Alice's public key, and if the verification is successful, then only message is accepted, otherwise it is rejected. Okay, so here as you can see, a digital signature needs a public key system. The signer signs with her private key and the verifier verifies with the signer's public key. Okay, so here a crypto system uses the private key and public keys of the receiver, as digital signature uses the private key and public keys of the sender, as I've already said. Okay, so now signing the digest. Okay, we can achieve both authenticity and integrity together by using this process. As you can see, if the Alice is sender and Bob is receiver, the plaintext or message is firstly passed through the hash algorithm, then the output of hash algorithm is basically digest is passed through the signing algorithm by using Alice private key. Okay, and that signature is send it back to the Bob, and the message is also send it back to the Bob, and once the Bob received that signature and message, Bob applies the same hash algorithm and applies the verification algorithm by using Alice public key, and both the signature is valid or same, in that case only the message is accepted, otherwise it is rejected. So let's discuss the security services of digital signature. So in this section we'll discuss about message authentication, message integrity, non-repudiation and confidentiality. So message authentication means the message is generated by the legitimate users. Okay, a digital signature provides message authentication. Yes, we have already discussed about this. And message integrity, it means that message during communication is not altered or modified in between. Okay, so we have already discussed about message integrity. So we can add hash algorithm to using the to achieve the message integrity. Okay. And next is the non-repudiation. So first of all, let's know about what is repudiation. So for that, I will give one example. If Alice sends a message to bank and asks to transfer money from her account to Bob's account, and later Alice deny that she does not send the message, so this condition is basically repudiation. Okay, and non-repudiation basically a user cannot deny that he or she does not transmit the message. So to achieve non-repudiation, here the trusted third party is introduced, which is called a trusted sender. So here Alice is the sender and Bob is the receiver, and trusted sender here, which is a trusted third party. So here Alice first sign the message by using signing algorithm and sends it a original message and signature to the trusted sender, and trusted sender verifies that message by using Alice public key. Okay, once the verification is successful, it sent back again the trusted sender sign the message by using private key of trusted sender, and send the message, original message, and the signature, which is trusted sender signature, send it to the Bob. Now Bob verify that message by using public key of trusted sender. So this is how non-repudiation can be achieved here. And lastly, confidentiality. So here confidentiality means message will not read by any illegitimate users. It is achieved by encrypting the message. So here the encryption is added. So Alice is the sender and Bob is the receiver. So Alice first sign the message by using Alice private key, and encrypt that signature, and encrypt the signature and message by using Bob's public key. Okay, and send the encrypted cipher text to the Bob. Now Bob decrypt that message, decrypt that cipher text by using Bob's private key, and verify that message by using Alice public key. Okay, so this is how confidentiality achieved here. And okay, this is all about digital signature. Later we'll discuss about different schemes of digital signatures. Okay, so thank you.